Good morning, my name is Andrzej Wasowski and I'll be talking about bugs in ROS-based systems. This is joint work with quite a large group of colleagues. I would like to especially thank Chris Timperley, who is first on the pictures here, who has been coordinating this work extremely well, and he was also he authored a few of the slides I'm using. So this large team of people from various areas of expertise in software engineering, formal methods and robotics decided to understand what kind of ROS bugs are there in the wild. So our motivation was to both be able to advise ROS developers with tools, tips and techniques how to make their systems more reliable, as well as to derive research directions and challenges for our future work. So we have already presented the work to the ROS community several times, including in the ROSCon conference. Now I'm happy to discuss the research challenges in the quality in robotics workshop today. So as a team, we analyzed in excruciating detail, I would say, 220 bugs from 8 ROS packages. As you can see, we have some packages that essentially implement the entire system distributions. We have drivers for implements or robots like robot arms and mobile platforms. We have another entire application, KRobot, and internal packages like geometry too. We've also looked at some closed source commercial packages from 2 companies in order to establish whether the problems that the closed source developers are experiencing are different from those that the open source developers report. And they weren't. For each of these packages, we have worked through the entire collection of issues and pull requests and analyze those that the developers clearly reported they were a bug, or that we could in a group achieve a consensus that they are a bug. In total, that means that in total we have studied more than 1,800 GitHub issues and pull requests, almost 1,800 GitHub issues and pull requests. We have selected 221 of these entries as bugs. The others were extensions, software evolution steps, etc. Then we have built a Docker image for each of these 221 bugs, which was actually fairly non-trivial because it required us to travel back in time. A bug was reported at a particular time, then it was fixed, and it's no longer present in the code today. So we had to travel in time to construct a software ecosystem, the right version of programming languages, all programming languages involved, because ROS systems typically use a few. The same version of the Ubuntu platform on which it was running, and the same versions of all the distribution packages in order to be able to reproduce the bug. So we have built this time machine, and we have built the Docker images for all 221 bugs. We have also studied the discussions on GitHub a lot, and we have read up wherever we needed the background material in order to be able to report to you about these bugs in detail and make understanding them easier for you. So what kind of bugs ROS developers encounter? Well, it turns out they encounter way more than we would like to talk about, extremely many, extremely diverse bugs. So we need a lens to simplify the discussion about them, at least in a short presentation like this one. I will be losing, in this very short talk, I can only pretty much talk about a very coarse-grained distinction between faults and failures, and then I'll detail the faults a little bit. So the background is due for those of you who are not familiar with the terminology. Let's define a fault as an abnormal condition or a defect in a component, in a software component in this case, which may lead to a failure of the entire system. Then a failure is something that occurs that stops the component from performing its required function. So there is a duality between these two concepts. A failure is an observable proof of a fault, and a fault is the root cause of a failure. So when a robot misbehaves, we are observing a failure, and if we want to diagnose why it's misbehaving, we have to understand the fault. In code, in robotics code, as well as in mechanical systems, failures may appear arbitrarily far from the fault, and this is the challenge of fault location in this domain. This is so to give you an idea how these 221 bugs distribute by faults. So which were the root causes in the system in the reported bugs in the studied packages. This is a high-level table. We have coded the teams of faults and failures for all the bugs, often with more than one code. And then we had extensive discussions to understand what are the root causes and what are the failures. And this is the result of the top-level codes. So we built a hierarchy of codes, and these are the top-level codes that we created for faults in the software in ROS. This is the only faults we could have seen in our method was the software faults. Of course, there are also hardware faults, but this we couldn't see by studying the GitHub repositories. So the largest group of faults is the general programming faults, typical programming errors that are not different than anywhere else, uncode exception, wrong types, etc., etc. Then the second larger group is the first two codes, which are the build, deployment, orchestration, so the build time problems and the runtime configuration problems. ROS is highly modular, and this creates lots of opportunities to misconfigure build or misconfigure your particular application, which consists of a unique set of nodes with unique values of parameters. This also makes it extremely easy to misunderstand the changing conditions. And so this is this fourth group here, evolution errors. 37 of them are configuration errors that and other errors that mostly appear because not of your code being changed, but the surrounding environment changing, other nodes in the ROS ecosystem being upgraded, or other components in the Ubuntu ecosystem being upgraded. That's a fairly large group of problems, 37 here. As besides that, we have seen concurrency issues. ROS is using callback-based concurrency with concurrency controlled based on locks. So this is also not entirely easy, and there are issues with synchronization, race conditions, and deadlocks, and often very expensive discussions lasting for long. We also see models problems which are specific to robotics. So either the robots are incorrectly described, their sizes and shapes and dimensions of freedom of motion, as well as the code that maintains the model of the universe inside the robot might be wrong, and then the model and the reality diverge, leading the robot to misbehave. Finally, we also have system errors that are outside software, or errors that arise from interaction of software and hardware. These we call system errors. So this is the high-level set of things we have seen. I think it's a little bit boring to talk only at high level, so let's look at a particular bug randomly picked from 221. The bug had a failure that resulted in unexpected movement. So the failure was unexpected movement, and the fault, so the reason, was the wrong calculation in the controller. This was on the Kubuki platform, which uses a differential drive, and the command velocities were provided as short integers and converted back to short integers after every calculation. Even though the calculations yielded floating point numbers, the rounding up and truncation errors accumulated, and this has led eventually to the robot moving forward, to the robot moving backwards instead of forwards when it was supposed to move forwards. So the failure the user can observe is that the robot moves in the right direction, but the actual fault or the problem at hand here that needs to be fixed is the wrong type used in C++. So that's a fairly extreme example of how far the failure and the observed failure and the actual fault lie from each other. Needless to say, we don't have fault localization techniques for this kind of problems at all in software engineering right now. For each bug, we provided such a description that I hope is understandable to you all, even if you're not building robots. So we have a short title, we have an almost layman description written more in software engineering formal methods terms than robotics terms. Then we have a bunch of fields out of which I am only choosing a subset here, some keywords to facilitate searching, some links to background material that we have used studying the bug, the phase, runtime, the application, mobile robot, in what languages the bug appears, and in what it has been fixed. This is actually abbreviated here. It's short, it's longer in the full bug description. We have a traceability link to the actual issue where this was discussed, the files in which it has been fixed, and the team codes that we have associated. So this has been assigned a fault in data types and in calculation, and the failure code as behavioral and the system behavioring. So the software has a behavioral problem, and as a result, the system is behaving incorrectly. So we have done this 221 times, creating a description like that. And what we have learned out of this is a very short, as for what I could do, summary of the lessons learned. So build deployment and orchestration issues are surprisingly prominent. This is and this is further exacerbated by the lack of type system connecting the various components and the heavy use of string names. So this allows for loose coupling of components, but also creates a lot of runtime or start type issues. So it would be good to have more lightweight checking tools for some of these problems, and or even program repair tools, because many of them seem to be fairly easy, and it would be easy to generate patches for them automatically and eliminate them from the ecosystem. One such tool developed by Andrzej Santos is ROS. Well, it doesn't do repair, but it does lightweight checking for these kind of problems, and it's increasingly popular in the robotics community. Concurrency issues with deadlocks and races lead to difficult Heisenbugs. People call them hundreds of entries in GitHub discussions by top-level community developers or members who are extremely busy and also respected in discussing how to reproduce an almost impossible to reproduce bug. So it would be much better to avoid these deadlocks that almost never appear, or these races that are almost impossible to reproduce, by working further to make ROS programming easy but safe. So give safety by design. There are projects that try to introduce ADA, Rust, and Erlang interfaces for ROS, which would be safer, and projects which introduce safer paradigms like reactive programming. But the challenge here is to make it these programming methods so that robotics developers can use them, so that it doesn't require a computer science degree to use these design methods, especially because most of the robotics developers in our experience have mixed degrees in mechatronics or mechanics and some software development. They can't be expected to use the most sophisticated software development methods. Then there are lots of coevolution issues. This is particularly difficult. So your system is not changing, but the environment is changing. And it's impossible for anybody essentially to see where problems will appear, because nobody has access to all dependent components in software and hardware. So some combinatorial and integration testing would be nice, especially in some kind of farm setup, so that it could be automated and reported automatically to projects. Yet this is super difficult for robotics. It's expensive, time-consuming, and it requires access to hardware, and nobody has all the hardware that ROS supports. Furthermore, we've observed errors that are very specific to robotics, so errors in robot descriptions, errors in units calculation, in transformations that lead to divergences between models and reality. So this seems to be a well-known challenge that we need programming language and static checking support for scientific and engineering computing. Here, for example, freaky units is a system that tries to achieve detects errors in manipulations of physical quantities in robots. But there is way more in ROS that one could do. Talking a little bit about failures, one challenge is that there is lots of failures that are difficult to diagnose in other ways than by humans. So these are errors in human-machine interaction, for which we have no automatic oracles. These are performance deficiencies. So the robot is too slow, too imprecise, too brittle, or maybe the torque is too high. There is there are also problems with partial loss of functionality. So the robot does perform, it didn't crash, but maybe it just doesn't perform optimally, or parts of its functions or actuations are not working. For most of these failures in these three groups, the only oracle that we know is human in the loop, and building an automatic oracle is very difficult, and it's not easier than building the system itself. I have never seen this being done. Building a monitor that checks all the physical quantities of the robot, for example, to make sure that none of them has that all of them have sufficiently good performance profile. And note that performance is not just a threshold. It might be, I don't know, a requirement on the integral over or average of the performance over a longer time, etc. This hinders automatic regression testing, and one has to admit that for system developers very rarely use automatic regression testing, and this is frustrating. Component developers outside the drivers world, they use regression tests, although they could use them more, exactly because not everything is easy to capture in regression tests. And this is particularly annoying because sometimes loss of functionality can just be an irritation, but often it could be also a catastrophe if the robot doesn't detect an obstacle, doesn't circumvent it, or perhaps performs an actuation that harms a human nearby. So it's also hard from testing and verification perspective to distinguish nuisances from hazards, which leads in many methods to false positives that basically bother developers with needless problems or innocuous problems. We need better methods to prioritize and to select and maybe compartmentalize designs and analysis methods so that we can focus on containing the risks and making the right parts of the system high quality, while we could give up the others. So simulation is of course a big help here, but as also shown in our bugs, it's at odds with needs of engineering because it's not precise enough. So this is the so-called simulation reality gap problem, which may mean that tests are passing perfectly, but in reality the robot does not perform as it should. All the other way around, some things are possible in simulations because simulations can also contain errors, and they are not sound approximations of the universe, but they will not be possible in reality. Just a very quick zoom in. Two problems that are specific to ROS, not maybe so much to robotics. So this is a distribution of languages in which the bugs have been fixed. And I would like to note that, of course, lots of them have been fixed in C++ because we looked at C++ projects, so that's not surprising. But about half of them have been fixed in other languages than C++, and most of these languages were domain-specific. CMake, URScript, URDF, the language for defining robots, Package XML, the language for defining components, Launch XML, the language for starting up components, the initialization scripts, and so on and so on. So this is all these small bars are domain-specific languages that were sort of underexploited in the software correctness research. Yet it seems that they are responsible for a rather large fraction of problems here, and they require completely different tools because nobody will build the same kind of quality tools for C or C++ as for URDF. So that sort of doesn't close with the number of users that URDF has against C++. So we need methods that are sort of meta methods that are possible to instantiate for languages efficiently. And similarly, this is a graph showing how many files have been touched when the bug was fixed, and this has been manually verified. So this is fault location, and we can see that most of the bugs can be fixed in one file, but there is a long tail of bugs that can be fixed in 2 or more files, up to 29 in our collection. So this is telling us that program analysis, fault localization, program repair tools should really work on more than one file, and this is really rare. And for program repair, I don't think I have seen a tool that is able to generate patches that cross more than one file. So all this data that we have collected is available in Robust, which is a GitHub repository called ROS bug study. This is the screenshot. It's actively curated right now because we are finalizing a paper about it. You can find it under this link. In the repository, you will find bug descriptions and scripts to rebuild the Docker images for all the bugs. In conclusion, I'd like to summarize what is that you can get out of Robust. So first of all, you can learn about bugs and issues in robot software, both small and big, safe and unsafe, in inclusive, non-specialist terms. You don't need to be a robot engineer to start understanding this. We give you layman descriptions, and we give you links to background reading and discussions if we had some and if it was necessary. You can understand how the problems you work on, let's say from programming language perspective like concurrency, or from verification perspective, traces or liveness, how they manifest themselves in ROS, so that you can find the corresponding examples for your work. You can find problems that can motivate your work from a real complex and extremely popular software system. You can find evaluation problems for your tools and methods. You can execute Docker images to access a piece of software that exhibits a bug, so you can actually run tools on the buggy version of the software. Or if you find other bugs in ROS's history, you can build new Docker images using our time machine to get the evaluation experimentation setup for your project. So as I'm saying, the data set is still being worked on, but it's already available under this link, and there is a manuscript coming soon. I think we need a small number of weeks to finalize it. 60 pages roughly right now of the analysis of the problems in the ROS ecosystem, and I obviously couldn't give justice to this analysis in this very short presentation. Thank you for your attention.